I spoke too soon. I think we need to do a bit of practice before we start graphing. So let's look at this. Here's a graph of a polynomial function. It is smooth and continuous. Can you answer these two questions here for me? Yeah, if you see one end is falling and one end is rising, you know that this is a function of odd degree. What about the leading coefficient? Is it positive or negative? I hope you can see that it is positive. If I think about the graph of y equals x cubed, I know that my graph falls on the left and rises on the right, just like this example. So what about the real zeros? A, B, C, and D are the real zeros. Now, where is the graph touching the x-axis? I hope you see that it's touching the x-axis at B. What does that tell you about the multiplicity for that real zero? It tells you it's going to be even. Because if I think about the graph y equals x squared, I know that it touches the x-axis, and that has an even multiplicity. The graph is crossing the x-axis at A, C, and D. Those will have a multiplicity that is odd, just like y equals x cubed, where it's crossing the x-axis. Sometimes you're going to be asked to find an open interval where the function is above the x-axis. So let's look at the picture of this graph here. I see that it's above the x-axis here, here, and here. But remember, when we're talking about the intervals, we're talking about intervals on the x-axis. So where is it above 0 on the x-axis? Well, it's above 0 from A to B, from B to C, and from D to infinity. Now notice when I wrote the interval notation for that I've listed this B separately because I'm asking where the function is above the x-axis. And at B, the function is equal to the x-axis, not above the x-axis. Can you find the intervals for where the function is below the x-axis? We see the function is below the x-axis from negative infinity up to A and from C to D. It's actually important that we're using open or round brackets here because we want the values where the graph is below the x-axis, not equal to. If I put a square bracket here, it would say it's below the x-axis at A, but it's not. At A, it is equal to the x-axis. We just want below. So we can say then in question 6 that the f of x is greater than 0 at these intervals where the graph is above the x-axis. Greater than 0 is the same thing as above the x-axis. So we have from A to B, B to C, and from D to infinity. Do you notice how the next question is a little bit different? Where is it greater than or equal to 0? Well, it's equal to 0 at A, so I'm going to use the closed bracket. It's equal at B, so I don't have to stop there. In fact, all the way from A to C included, it's greater than or equal to 0. And then at D, also equal to 0, continuing to infinity. Try answering question 7. Where is the graph less than 0? Where is the graph less than or equal to 0? So again, less than 0 from negative infinity to A and C to D. Less than or equal to 0, I need to include A, and I need to include C and D. So be careful when these questions are asked that you read for exactly what is being asked for. We also should talk quickly about the maximum number of turning points. If we look at this example of a function, a polynomial function, we see that it has real zeros of 4 and -2. So that tells me that somewhere between +4 and -2, somewhere in between there, the graph is going to have to change direction. Right? If the graph started increasing, at some point it would have to decrease to get to 4. If the graph was decreasing, at some point it would have to increase to get back to 4. The point at which a graph changes direction is called a turning point. So we're not going to know exactly how many turning points there are, but we will know the maximum possible turning points. So we say if f is a polynomial function of degree n, then the graph has at most n minus 1 turning points, one less than the degree. We say if a graph has n minus 1 turning points, then the degree of the function is at least n, at least one more than the number of turning points. Look at these examples. In the f of x, we see that the degree is 4. That means the maximum number of turning points is 3. Can you find the maximum turning points for the h of x? We saw that the h of x has a degree of 9, so the maximum turning points is 8. What about for the k of x? I hope you weren't fooled by this one. This function is already opened. It's in standard form. The degree is its highest power, or 3. So therefore, it has a maximum of 2 turning points. Look at the last question. The graph of a function g has 4 turning points. What is the minimum degree of the function? So we know the 4 turning points. What's the maximum, or sorry, what's the minimum degree? Remember that the minimum degree is 1 more than the turning points. Think about the graph of y equals x cubed. We know it has a maximum number of turning points of 3 minus 1, or 2. But this graph doesn't turn 2 times. In fact, it never changes direction. So the maximum turning points isn't how many times it will change. It's just the maximum it could change.